Hey guys, this is Yashwant Vijay Kumar. I'm a project lead at Adobe Experience Platform for the Unified Profile team. Today, we're going to talk about everyday probabilistic data structures for humans. Specific emphasis on the humans part. You'll kind of see why. Um, Today's goals, I want to keep it as simple as possible. The first one is to add some interesting tools to your data processing belt. The second thing is I want to, instead of just introducing you to it, I also want you to show how to use the tools and apply it. So what's not in scope is the internals of the data structures. There are way better resources than me who know what they're doing and what they're talking about. So I'm going to leave it to them. So this is going to be mainly from an application point of view, so that at the end of this talk, you will feel like trying this out on your own. Um, as part of our daily, engineering lives, I would say the three pillars that we always constantly keep looking at is cost, latency, and accuracy. How are we trading off these three things in order to, get our final goal? That kind of is like the daily theme of our lives. Um, when I said for humans, right, we need to make sure that this is what to say, it echoes well with you. So we're going to take an e-commerce company as an example. Let's take Rainforest Inc. Um, we're going to look at a simplified event workflow that they have. A user logs into the page, they visit a product page, they add some stuff into a cart, and then they purchase it. And then we see events get generated for it all the time. Now, if we were to take a look at what such an event would comprise of, the significant fields would be like the product ID of the product, obviously. With respect to event types, it would be an enumeration of, say, page visit, add to cart, and purchase. And also the user ID who is clicking into these pages and making these actions. The total price, and then the seller ID to indicate who's actually selling this, and then also the IP address. Um, Now, with respect to the scale of events, to just kind of give a context as in why we make certain design decisions throughout the talk. Uh, you can skip everything else, but the main thing that I would actually pay attention to is like the size of the daily events that is kind of flowing into our system. So it's like 1 TB of data. So a lot of you right now would be like, hey, 1 TB is not a lot. But then compounded with factors like, say, if you're going through like, say, 30 days of data, 30 TB adds up pretty quickly. If you're making repetitive queries for data that's constantly streaming in, you're going to see this add up pretty quickly. So now that we've framed our hypothetical company, let's also frame some hypothetical product requirements, right? The first thing is, has a user visited this product yet? The second question would be, how many unique users bought items A, B, or C? And then the third question would be, how many items has seller X sold today? Simple enough. So now what we're going to do is we're going to have these three questions as our base. And we're going to use certain data structures to answer these questions in kind of like a cost and latency effective way. So what are we going to trade off right now? Like we're going to kind of give up on accuracy and going to go very heavily on reducing cost and reducing the latency to answer our questions. So to get into probabilistic data structures, uh, the three data structures that we're kind of going to look at today are Bloom filters. The next one is Hyperlog logs. And the last one is count min sketches. We're going to go kind of like semi-deeply into these and going to focus mainly on like the implementation part and the end-to-end design part as in how to use these. So let's start off with Bloom filters. With respect to Bloom filters, like I said, we're not going to go, too deeply into how Bloom filters work, the internals or whatever. I'm gonna, all of my the slides, they're going to refer to like the talking points with respect to even if you don't listen to anything else, just follow these points, and I think you will be able to utilize them at least once somewhere. So it mainly answers the set membership question in a probabilistic way. I would look at it as a replacement for, say, like a normal set.exists of key, if you're looking for a one-to-one comparison. The main question it translates to is the element that I'm looking for possibly in this set? Notice the emphasis on the possibly. If yes, what's the probability that the answer is wrong? If the answer is no, in that case, you are guaranteed that you definitely don't have it in there. And the last important thing, which will make a lot more sense in the next few slides, is loss-free unions. That is, we are able to combine them in a loss-free way. So given that, right, we're going to sidestep into like abstract algebra, where we're going to go through like a category of data structures called like monoids. And this is going, it might be like, wait, we were just talking about Bloom filters. Why are we jumping to monoids? Trust me, it's going to make some sense as soon as we finish this train of thought. So with respect to what monoids are, um, the way I would look at it is that given that you have a set M and an operation OP that we have defined, we're going to look at various properties that are there, whether it has closure. That is, when you do two things, as in when you perform an operation with two elements, does it still belong to the same set? That's the closure property. Like for example, string A plus string B gives string AB, which is again a new string. The next one would be associativity. Basically, it tells you that the order of grouping for the operation does not matter. Like string A plus B plus C, no matter how you group it by, the final result is ABC. So that's one example. And the last and one important thing is the identity. So such that if you perform an operation with the identity element, you still end up with the same thing. So in the case of a string, if we were to take an example, it'll be like an empty string. So any string A plus an empty string, no matter which side it comes on, you still get string A. Okay, so now that we're done with monoids, let's get into, let's now put together monoids with Spark before we get into the Bloom filter layer. When you look at the map reduce boundary, basically the shuffle, aggregate functions in Spark specifically, like sum, count, they kind of trigger shuffle in in order to move data which is locally aggregated in one node to to kind of get across the node global computations. So you can see like each executor produces local aggregates, and then the local aggregates get put together by the shuffle process in order to get the final computed aggregate. Now, if you put together this with the monoid fact, it will make a lot more sense because we are, the properties of the monoid exactly help you define a very simple aggregation function. So in other words, if you have a monoid, if you have a data structure which is a monoid, it's a very easy way to say that you can convert it into a Spark aggregation function. Now, keep that in mind and let's see. So I went ahead, forget this entire wall of text over here. I went ahead and wrote my own Bloom filter aggregator. Nothing big, but then if you focus on the first part, which is the 0, so you can see that this is the identity element where we're just creating an empty Bloom filter. And the second part, you would see that the merge step, where you're taking two Bloom filters, like B1 and B2, you put it together, you get another Bloom filter. So here, what helps is the associativity and the closure property. So now that we've exactly seen how monoids help in aggregations and how we're able to express a Bloom filter as a Spark aggregate, we can easily see that it becomes trivial to express it as an aggregate function to use on top of our data frames. But the good thing is Spark already took care of it in a way. Like using the data frame stat functions, they already have a Bloom filter implementation. So all I need to do is Bloom filter off whatever column you want and the extra set settings, and you can create a Bloom filter for it. No worries. So next, what we're going to do is how do we exactly use this Bloom filter to answer one of the questions that we have. But before we get to that, right, I just want you to pay attention to this slide, because what this is going to tell you is, while there are a lot of examples showing Bloom filters, Hyperlog logs, count and sketches, they all show it in a batch fashion. Sure, you have a bunch of data residing in a data lake, you load it into a data frame, you create some filters out of it, you're done. But then, a lot of the times in real life, it doesn't exactly help, because we have data streaming into our systems all the time. Take, for example, the Rainforest Inc. case. You have data flowing in all the time, and you can keep, orchestrating like a batch process that keeps incrementing these Bloom filters all the time. But then at some point, we kind of want like a neat framework to keep doing this incrementally, so that we don't need to go scan all the data again and again. So what we're going to do is we're going to use Spark streaming. Now we're going to create our sketches in or the probabilistic data structures in the executors, and we're going to write it to like an external store constantly. So for every microbatch that keeps going on, say like for every 30 seconds or something like that, we're going to gather the data and write it to an external store. And then the apps, and you can have any amount of apps reaching out to the external data store and consuming these probabilistic data structures to answer your questions. So now, given that, and that's set in stone, let's get into actually answering some questions now. So has the user visited this product yet? If we look at the ingestion workflow, before we get to the code, let's just do a small step through for the pseudocode wise. So for every ingestion microbatch, that is, say, if our trigger interval says 30 seconds or something like that. So every 30 seconds, we're going to get a data frame with a bunch of rows. So what we will end up doing is we're going to create one Bloom filter for every product. So if you have P1, you'll have P1 hyphen Bloom filter created for it, and so on. In the map step, we are going to create, we are going to use the key as the product ID, and the value emitted will be the Bloom filter. In the reduce step, we will combine all the Bloom filters from each partition and get it into one. And in the for each batch state, we are going to update it to the external store. So at this point, I want to switch over to show a demo that I have. So I have a notebook where I have defined our event class over here. So our class event, so it has a product ID, event type, user ID, blah, blah, blah. So you can take a look at an example structure of this, like product 5610, add to cart, user that purchased it, and so on. I went ahead and generated some synthetic data already. We're not going to go through all of that right now. The external data store that we're going to use for all our demos is like Redis. So that connection has been set up already. If you're familiar with the Spark pane of encoders and output encoders, this will feel very comfortable for you for Cryo. To simulate the data into the stream, I already wrote it into Parquet files. So I'm just going to read it into an event stream, and that's what we're going to run out of. So getting into the Bloom filter part, to create the Bloom filter, if we go line by line, what we end up seeing is that for every batch in the event stream, so we get a handle on the batch data frame and the batch ID. We're going to spin up first the list of unique products in a given batch. So once we have that, we have the list of, for every micro batch, we have P1, P2, and P3. Now, given that we have the list of unique products, now we know that for this micro batch, how many Bloom filters we are going to create for the micro batch. So for each, what we're going to do is we're just going to use As in, to keep things very simple for our demo, we're going to use the Spark Bloom filter. So once we know what product it is, we're going to create split data frames per product, and going to create a Bloom filter per product. And then what we're going to do is we have a convenience function here called update Bloom filter, which updates it for every product. And this is the key structure that we're going to use for the Bloom filter. We're going to take a closer look at the update Bloom filter part, because that's going to tell us how exactly the monoid properties actually help out for this. So if you look at the update Bloom filter, you can see that it takes in a new Bloom filter and then also takes a key. So first, what we do is we check if there is already a Bloom filter in Redis. If it is available, in that case, what we do is we fetch that, and then we merge it in place with the new Bloom filter. And then if the Bloom filter does not exist, say in that case, it's much more simpler for us. We just, what would you say? Put a new one over here. So this would be the zero property, and this would be the associative enclosure property. So we just are using Redis as our external shuffle mechanism in a way, in order to make this more efficient. So since this is what do you say in a presentation, I didn't want to start the stream right now, but I already ran it ahead of time. So what we're going to do right now is we're going to query the Bloom filter. So we already populated the Bloom filter with the thing, but then we can query it at live. So let's see what question we had. So if we look at the entire data, right, we can see that we have it something like, okay, let's look at for product ID 8788. If I did a filter for that, I see that we have a good amount of entries over here. And then I can see a good amount of users have also, what do you say, gone through it. Now, if I want to check if a particular user has actually, visited this product, all I need to do is fetch the Bloom filter for this product. This is again a convenience function for this, and we call the might contain on top of it. So what would you say? Oh, looks like the cluster got shut down. But yeah, no worries. We just ran it sometime back, so the results pretty fresh. You can see that, what do you say? We can see that the result is true, that this is available over here. The key thing to note over here is the timing. So this took only 0.16 seconds versus this taking 1.79 seconds. As we get more and more data, this time will linearly increase. No matter how many indexes or whatever you're going to put, if your queries have like a full table scan kind of nature, this is going to increase linearly. But then this query is going to remain constant, because in terms of the actual operation, this is a fetch from Redis for the Bloom filter, and then an actual operation on top of the Bloom filter. So this is quite efficient in that way. So this should give you a good idea. This basically translates to a set.exists. Exists. So we're going to go over Hyperlog logs now and see how it helps us answer the next question. Again, if we were to take a 10,000 feet overview on the Hyperlog log, let's see, the main question that it answers is how many distinct elements do you have in the set? This is analogous to a set.count, so that you can see how many unique elements are there. The great thing about the HLL is that you can estimate amazingly large cardinalities with a very good amount of accuracy using just 1.5 KB of memory. Of course, you can put in a lot of different, features on top of it, and flags on top of it, and trade off for accuracy versus space. The other neat thing is loss-free unions, like we saw for the Bloom filter. And again, it's a monoid. So all that boarding theory that we heard in the beginning, all of that translates over here to see like why HLL becomes a very simple aggregate function in Spark, or any distributed computation, for example. So I know a good amount of people in the audience are going to be like, okay, wait, they both look pretty similar. Like you kind of use set as the common thing over here. What's a huge difference between when do I use one versus others? So without getting into too much of details, I would kind of put it into two blanket rules like this. For cardinality estimation, HLLs are better as you keep adding more elements into it. This blog over here has some very good plots showing that. For membership testing, you use a Bloom filter. There is no other, as in, it's just super simple. So now, getting to, we said, oh, a HLL is a monoid, right? So in terms of support operations, you add a hash to an HLL, you still end up with another HLL of 1.5 kbp. The merge and the cardinality operations are again like very symbolic of the monoid, and the cardinality being very specific for the HLL itself. So getting to the question that we want to answer, right? How many unique users bought items A, B, and C? So if we were to again go through the ingestion workflow, we will see that on the ingestion microbatch, similar to what we did for the Bloom filter, we're going to create a HLL for every product ID. And then this is where we're going to slightly start deviating from the previous approach, where we were doing a good amount of the Bloom filter creation within Spark. But in order to keep things a bit fresh, what we're going to do is we're not going to do the data structure population inside Spark. We're actually going to take it outside to just expose you guys to another pattern. So in the for each batch, you're going to group by product and do a local aggregation, and then of use users. And then we're going to update it to an external store, where in our case, where Redis is the external store. And we're going to have the HLL actually as a data structure inside Redis. That's one cool thing that I like about Redis. I'm a huge Redis fanboy. So you're going to see me, gush over it all the time. So enough of talking, and let's actually get to the second part of our demo to get to about the HLL part. So similarly, for HLL, what we're going to see is we're going to go over the event stream. And for each batch, that is, we're going to get the handle on top of the micro batch data frame, which is going to have the events that have happened in that micro batch, in that time interval. Once we get that, we're going to get the mapping of products to users. So basically, it's group by product, and then we're going to make sure we filter only for the purchases. So the final output would be like the mapping of product ID to user 1, user 2, user n, with all the people who actually purchased it in that micro batch. So now that we have this, right, what we're going to do is for each product in this derived data frame, we're going to push to Redis as a HLL, a purchase HLL for each product. So product 1 would have a product 1 hyphen purchase HLL with the list of users who have purchased it in that micro batch. Now, the key difference here is like we are directly pushing it to Redis, right? So some keen observers would notice that this is kind of similar to since we have a local aggregation here for this micro batch for the product, this is kind of like equivalent to a combiner step. So we've already gotten a combiner step, a combiner output over here. So all we do is just push it to Redis. So now the key thing here is, again, the monoidal nature comes into play, because you could have multiple threads actually pushing data for the same product or product. But then it doesn't matter, because even if you have 3 operations for the same product getting queued up on Redis, since it's single threaded, the associativity property for the HLL would kick in, and no matter what order of operation it happens, the end result of the HLL is still good. So that again is how being a monoid is going to help us in terms of scaling it out over here. So what we effectively have is, as and when the data is coming in real time, we are updating our Hyperlog logs for each product with the list of users who have actually bought the product. So again, similar to the Bloom filter, I already populated it ahead of time. So what we're going to do is, first, let's take a look at the actual data. So that sets the context to compare it with what we're going to query, right? So if you look at the full purchase data frame, where we're grouping by product and we're looking at only at purchases, you can see that you get a list like this: every product and the list of unique users who have bought that product. So now, given this is the actual data. Okay. Now what we're going to do is we're going to use the pf count method to access a given product's hyperlog log. And we're going to see how many entries are actually there. That's the entire bread and butter use case um, for the Hyperlog log, right? Cardinality estimation. So you can see that this has 5. So cool, we got some answer. This product exists, and we got, so you can see 1619, yeah, 1, 2, 3, 4, 5. Okay, so far so good. Accuracy is not being traded off yet. So that's fine. So the next thing, but then the actual question that we wanted answered is users who bought, as in the total set of users who bought A, B, and C, right? So what we're going to do is we can perform a union operation with the HLS, because we already saw that merge operation, right? So what we're going to do is we're going to look for product 1619, 4944, and 3939's HLLs. I'm going to combine them and see what the total count for it is. So we got the count is 21. Now say if we do a query on top of this data frame for only these specific products that we have mentioned, what happens? So I already done that ahead of time. So we can see that, let's look at the count. So this finite, like, yeah, 22, unless my math's going really bad. So yeah, so but this is 22, but then we got 21. But the key thing to note here is that we are looking at, how should I put it? A union. So if you look at this example, product 4944 and 3939, they have a common user here, 12415 and 12415 here. So we can't double count them in the union. So we actually got the right answer over here. So good stuff over there. So yeah, and again, similar to the Bloom filters timings. So this took 1.68 seconds after we already generated this data frame, which initially took 35 seconds. So because with the group by and all that stuff. So, but then this took a constant 1.14 seconds. So I can guarantee you that no matter how many more entries you add, as long as our configuration is right, for the Bloom filter, we're always going to get an answer kind of like around the same ballpark. But then this time, 1.68 plus 34, like 37, 40 seconds, this is going to keep increasing as you're looking at more and more data over the days. So again, we traded out, as in we have gotten now a nice data structure through which we are updating it in real time, and we're able to get answers in real time by trading off a bit of accuracy over there. This is a good amount of compression here. So now let's switch over to the count and sketch section to try to answer the last question that we have. So for account and sketch, again, if you look at a 10,000 feet overview, I would look at it as a space efficient frequency table, or to look at it in very plain terms, a hash table replacement. Again, I'm dumbing this down really thing, but so please do apologize. I do apologize if people see this as too much of a generalization. But yeah, the next thing is, oh wait, space efficient. Then what do you mean by space efficient? So it takes sublinear space instead of order of n. Good for us. You might lead to some overcounting, but that's fine. We are saving a good amount of space here. The technically logical extensions of Bloom filters, when you start digging down into the internals, the cool thing is it's monoid. again, can't emphasize enough how important as in it being a monoid is for our use case, specifically with Spark. So now that we saw that, okay, accountment sketch is a frequency table, a hash table replacement. Let's try to answer the question, how many items has seller X sold today? This is nothing but a frequency question, right? If you were writing a SQL query, you're going to be like, yeah, select star from table, or like you're going to be grouped by seller, and you're going to be getting the count based on the seller ID. So going in with the same, workflow or the end-to-end design that we have, let's look at the ingestion workflow for this. For the ingestion micro batch, what we're going to do here is we're going to create a countment sketch for the seller count per date. But then the key thing is we're going to create a countment sketch for every event type. Because if you know the question here, it said, how many items has seller X sold today? Like each seller, because of the products that are associated with it, they could have 3 different types of events associated with them. So like a page visit, an add to cart, a purchase. So what we're going to end up doing is, if we want seller-wise statistics, why not just generate a countment sketch per event type? So once we generate that, the reduce step becomes very simple, where we're just going to merge in place the list of countment sketches we get from each executor. And then in the for each batch, just like what we did for the Bloom filter, we're going to update it to an external store so that it can be served and consumed by other services. Let's switch back to the demo to see how it actually works. So for the countment sketch, we again created a helper method to update the Redis for that. But then let's look at the boilerplate code that we have. This is exactly similar to the Bloom filter code. The only difference is wherever I see, as in, instead of doing it for the products, I'm doing it for the event types right now. And instead of Bloom filter, we're creating a countment sketch. But apart from that, it's kind of a word by word copy. I just changed the variables, to be very honest, and it works, which is good. So what we end up doing is, for each batch, for each micro batch that we have in the data frame, in the micro batch, what we do is we get the list of unique event types in that micro batch data frame, and then we do a split by getting sub data frames per event type, and then we end up creating a countment sketch using Spark's own data frame stat functions on the seller ID column. And once we get that, we update the countment sketch in Redis. So again, this is exactly similar, where we check Redis to see if an existing countment sketch is already there. If it exists, we fetch that and merge it in place and write it back. If it doesn't, it's a simple 0 case. So we just write it into Redis freshly. So I already ran it through for our the data that got generated. Now let's look at the actual data with respect to the group by conditions. So I group by seller ID and event type. So on top of the whole data, when you look at it, we can look at, okay, seller 1169, purchase 23, blah, blah, blah. So we have an actual frequency table. This took around 2 minutes and 30 seconds. Key thing to note is event df is already cached right now. So all the subsequent queries are happening pretty fast. So now what we're going to do is, using the helper function for the countment sketch, we're going to fetch the add to cart countment sketch for the seller. And once we have that, we're going to look at seller 675. So 675 and add to cart. Let's see how many he has. Add to cart, so he has 21. But then here 675 has 27. So that's kind of odd. So it's fine. It's still around the same ballpark. So we're kind of okay with it. So what you can see is we are able to we got a single add to cart count with sketch, and I'm able to estimate the count of a particular seller that I know exists inside that. So again, if you look at the time, 0.13 seconds, this is guaranteed to be around constant as long as your Redis doesn't crap out. So another thing that we can do is, okay, let's now that we have the count when sketch for add to cart, can we see how many total events did we actually add to cart events are there for the sellers? So we can look at it. The estimated number is 49,000. And when we run a query for that, we can see that it's still 49,000. So good. Again, we saved a heck ton on time. We updated it in real time, and we are able to get estimations in real time without having to run these queries on top of the entire data all the time. So now I think we were able to answer all the questions, with a good amount of accuracy. Of course, the data here, I just used like a million entries. So ideally, I wanted to use, say, like more, but then hopefully that drives home the point that these data structures can be used in various combinations to get to answer common questions that you have. Now, if you were to go back to the slides, right? If you were to look at the usefulness, the main thing that I want to drive home is that using these common patterns, you can optimize, like, if you know a particular query is going to get asked multiple times, and if it's expensive, instead of trying to, add multiple join conditions, or like, oh, let's do broadcast join, let's do hash join, merge, sort merge join, and all sorts of, let's do extra partitioning. All that's good, but then if you are looking at, like, like real time responses, it's good to trade off the accuracy bit with the cost and the latency bit using the probabilistic data structures that we went over. There are a lot more interesting data structures, but then these three I use quite often, so that's why I'm going for it. With respect to common examples where we could potentially use this, right? We saw for the hypothetical Rainforest Inc. One place that I see that this we can use is ML training. So a lot of the times, the features that get built, they're very expensive. They take you have these huge bad jobs running and crunching the numbers and generating this feature matrix. Instead, if you identify some certain aspects of it, you can, just plug it in with the probabilistic data structures. Another thing is page personalization. Take the example that we use right now. Like, we can have a custom background based on, say, a seller threshold. Say if a seller sold more than 5 items a day, make it green. Okay, obviously I shouldn't be a product designer or a UX person, but then you get the point. Another cool thing that I would say is a bit more unconventional. Say if you're looking for, bad or like leaked password lists and all that stuff, you can build, say, a Bloom filter out of it and ship it to the client. So you don't need, on every keystroke, you don't need to keep making unnecessary over the wire server calls to check if this is a bad password or not. You can ship that logic into the client itself. It's 1.5K baby, and it's way lesser than the background image that we have right now. So that's all that I have, mainly. If you guys have more questions, feel free to reach out to me at my email. I am going to upload the notebook that we have here, so that you guys can try it out on your own, and hopefully it's useful. Uh, all the examples that we went through were all toy examples, but then in the Adobe Experience Platform and in the Unified Profile team, we are making this a very generic and a reality to use these sketches at scale. So there is the profile summaries feature is powered entirely by the sketches. And it's basically a sketch as a service on top of marketing data. So look out for a blog on the Adobe Tech blogs for that. That's all that I have today. Thank you.